Hello, welcome back to another Taste of Physics with Aragoneses. I've talked about complex systems before in this channel, systems that are made up of lots of many elements that they do interact non-linearly. They are in the presence of noise and with time-delayed signals that affect all temporal scales and all the scales of intensity and space. Systems present emergent behavior that cannot be explained by analyzing the behavior of its constituents. Another surprising fact of complex systems is the fact that, despite systems being very different in their structure, they share dynamical behavior. This is fascinating and very important to study and characterize. In this paper published in 2024 in the journal Entropy, in collaboration with students Marcos Acero, Son Lyons, and Carleton College professor Argento Pataniak, we applied a geometric approach to find signatures of universality in chaotic maps. Chaotic systems are deterministic in nature, although they can include a significant amount of embedded noise. They frequently present dynamics that cannot be distinguished from randomness with traditional techniques. Nevertheless, underneath the apparent randomness, they can contain dynamical constraints related to internal temporal symmetries. There is a variety of measures that quantify temporal correlations in the output signal of a complex system. Each measure can capture a different aspect of the underlying dynamics. Permutation entropy, Fisher information measure, horizontal visibility, dispersion entropy, improved permutation entropy, or TARDIS are just a few of them. We recently introduced a visual symmetry space that locates the dynamics of a system in a three-dimensional space that captures temporal symmetries in combination with permutation entropy. Let's see what all this means. For example, permutation entropy is a complexity quantifier based on temporal correlations among consecutive events in a time series. It is computed based on the probabilities of some ordinal patterns or words composed of correlations among events in a time series. These words or ordinal patterns are computed by comparing relative values of consecutive events in a time series. This allows to transform the time series of some signal into a sequence of words and then analyze the language of the complex system. We can compute words of dimension 3, for example, and obtain 6 different words, which is the same to having 6 different temporal patterns identified. We can then compute the probabilities of each one of these 6 words. Permutation entropy is just Shannon entropy computed with the probabilities of these patterns. This figure shows the word's probabilities of words populations for the logistic map as a function of its control parameter R. It is interesting how for some values of R there are some words that are forbidden. Notably, word 6, the red word, does not appear at all for any value of the control parameter. Among all the chaotic behaviors of the logistic map, there are some regions, like this one here, that correspond to a window of periodicity. If we plot the permutation entropy, we can see a drop in entropy in these windows of periodicity. If we combine pairs of complexity quantifiers, we can track the system as it evolves with R. Here we plot Fisher information measure versus permutation entropy, and also reversibility versus entropy. This landscape tells us the story of this chaotic map and allows us to distinguish families of chaos based on its behavior on this space. One key finding using this technique is that other chaotic maps like the sign map, the cusp map, the tent map, the cubic map, or recurse map, they all lie on top of each other in this space. Despite being different maps and being defined with differentiated mathematical equations, they all share the same structure in this space, sharing universality patterns in the underlying dynamics. We obtain the same result if we use other complexity quantifiers like rotational hierarchy or mirror hierarchy, some quantifiers we introduced in this paper published in the journal Chaos in 2021. Each one of these complexity quantifiers captures a specific feature of the dynamics of the system. But considering the 6 words of dimension 3, there is a limited number of possible symmetries. Because these 6 words are time reversible of each other by pairs, we build this 3-dimensional space based on these time reversible pairs. We then plot the dynamics in this 3-dimensional space. These figures show for the logistic map. The color indicates the control parameter R. We can see how for low values of R, the system moves near phi1 equals to 0. It follows a few well-defined curves. It then jumps and increases the value of phi1 and evolves in this space. The pink dot indicates the dynamics of a fully stochastic system. Here we can also identify and classify families of chaos based on the location of the dots and their symmetries and differences with other dynamical regimes. One advantage of this projection is that the square of the distance to the origin is the permutation entropy. If we plot here the other chaotic maps we showed before, we see how they all lie again on top of each other. The advantage of this projection is that each axis indicates a very specific temporal symmetry. Our results reveal a universal pattern in the temporal correlations across all the chaotic systems studied. This pattern emerges regardless of the specific combination of complexity quantifiers used. While each combination retains its own distinct signature, the chaotic maps share a consistent fingerprint in every representation space. Not only do these techniques allow us to identify similarities and differences across chaotic dynamics, classify families of chaotic behavior, and uncover universal patterns, but they also connect these patterns to the system's intrinsic dynamical symmetries. Moreover, for chaotic systems exhibiting this universality, the evolution in symmetry space enables us to track where the system originates and where it is heading in the parameter space, offering potential for forecasting dynamic transitions. The techniques presented in this paper provide complementary information and strong evidence of the universality features that all these maps share, while they are not computationally demanding. You can access the paper here. Please let me know if you want to know more about it. Take care and may science be with you.